Welcome to the Explainer. Have you ever stopped to think about how computers manage to talk to each other securely across the wild, open internet? I mean, really think about it. This isn't just some nerdy technical detail. It's the invisible glue holding together remote work, the cloud, well, pretty much the entire modern internet. So today, we're going to pull back the curtain on the digital handshake that makes it all possible. SSH. All right, so here's our game plan. First, we're going to tackle the big problem SSH was born to solve. Then, we'll look at the surprisingly simple conversation that gets everything started. After that, we'll check out the different ways you can prove you are who you say you are, and we'll do a deep dive into the absolute best method. And finally, we'll see how to add another deadbolt to our digital front door to make it even safer. So let's start with the core challenge, right? The internet is basically a gigantic, super crowded coffee shop where anyone can eavesdrop on any conversation. So how does your computer connect to a server way over there and prove it's really you without some hacker listening in and grabbing your login details? To make this super clear, let's use an analogy. Just imagine the server you want to connect to is this exclusive, high-security club. And right at the door, there's a very, very strict digital doorman. Your entire job is to convince that doorman to unclip the velvet rope and let you, and only you, inside. Okay, so how does this little chat with the doorman even begin? You might think it's going to be super complex, right? Well, actually, the entire authentication dance is built on a simple back and forth, using just 4 basic types of messages. And what I love about this is just how simple it is at its core. Your computer, the client, just walks up and sends a request. It's basically saying, hey, I'd like to get in, please. The server, our doorman, can answer in one of 2 ways. A failure, which is a firm nope, try again, or a success, which is welcome, you're on the list. And if you get in, the server might send you a banner, which is just a little welcome message. That's it. That's the whole framework. So, we know the basic script, but how does your computer actually make its case? What does it present in that initial request to prove it belongs there? Well, turns out there are a few different ways to get past the doorman, but let's just say they are definitely not all created equal. The source material shows us these main options. You've got the password method, which we all know, just a secret word. There's host-based, which is kind of like the doorman letting you in because you showed up in a recognizable, trusted limo. And then there's none, which is, well, it's like leaving the front door wide open with a come on in sign. Not a great idea, but we're going to focus on the real star of the show, the public key method. And this slide right here gets to the absolute heart of why this matters. Using a password is like shouting your secret word across that crowded coffee shop. If anyone overhears it, boom, your security is toast. The public key method, on the other hand, is just so much smarter. It lets you prove you have the secret key without ever having to shout it or even show it to anyone. So let's zoom in on the main event, this lock and key method. This is so fundamental to SSH that the official rules say it has to be included in any SSH software. It's not optional, and for a very good reason, it's the gold standard. The whole system works with a pair of keys that are mathematically tied together. First up is your public key. The best way to think of this is like a really special custom-made padlock. You can make as many copies of this padlock as you want and give one to every doorman at every club or server you ever want to get into. It's public. Anyone can look at it. No big deal. But then there's the second piece, and this is the crucial one, your private key. This is the one single master key in the whole world that can open all those padlocks you've been handing out. You guard this thing with your life. Seriously, you never share it, you never copy it, you never let it out of your sight. This key is the ultimate proof that you are you. So here's the genius part. When you try to log in, the doorman doesn't ask to see your secret key. I mean, that would defeat the whole purpose, right? Instead, he takes that public padlock you gave him and creates a unique challenge. It's like he builds a tiny, complex puzzle box that can only be opened and signed by your one-of-a-kind private key. And this table shows what your computer sends back to the server. You've got the basics in there, your username, the service you want, the type of key, but the real magic, the mic drop, is that very last item, the signature. That is the solved puzzle box. It's the cryptographic proof that you, and only you, have the private key that could solve the doorman's challenge. So, the doorman gets your response, uses his copy of your public lock to check the signature, and click! It matches perfectly. He knows, without a shadow of a doubt, that you must have the private key.
He's totally convinced. He sends back that SSH_message_user_off_success message. The velvet rope swings open, and you're in.
Now, having a nearly unpickable lock and key is fantastic. It's a huge security upgrade. But what if you want Fort Knox level security? What if someone, somehow, managed to steal your laptop and your precious private key along with it? Well, that's where we add a second lock to the door, a little something called multi-factor authentication, or MFA. Using our analogy, this is like the doorman checking your signed puzzle box, nodding, and then saying, "Great, one last thing. Show me the 6-digit code from the Authenticator app on your phone." On the server side, this is usually set up with a really flexible system called Pluggable Authentication Modules, or PAM. Just think of it like a universal adapter that lets SSH plug in to other security tools, like Google Authenticator, without having to rebuild the whole thing. And these temporary codes usually come in 2 main flavors. The most common one is TOTP, which stands for time-based. This is the one you probably know, where the code on your app refreshes every 30 seconds or so. The other is HOTP, or counter-based, where a new code only shows up after you use the old one. Both are awesome and add a really powerful second layer of defense. So there you have it, the secret behind the secure digital handshake. It's not about whispering a password. It's about proving you hold a unique, unshareable key. And when you combine that powerful idea with a second factor of authentication, you can build a digital front door that is incredibly tough to break down. Which leaves just one question: how secure is yours? Thanks for watching.